right. And I think, okay, I can run through this one. So we've got 15 disks, which are all stacked together. And to solve for the moment of inertia, we need a couple things. So if I've got 15 disks, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And the center is there. And so they're all rotating about their central point. And so we want our full moment of inertia. And so it says that our mass is 135.0 grams, which is equal to 15 times our little masses. So each of the little masses. And our length is 1.4500 meters. And if we look at the little, if we expand one of the little circles, so we have an R, then each one will have a width of 2R, and so this is 30R. Okay, so that will just help us for later. The distance between each of the centers is going to be increasing in increments of 2R all the way up to the last point, which is going to be 2, 4, 6, 8, 10, 12, 14R away from the middle. And again, that will be helpful in a second. So the moment of inertia about a disk, about its center, is mr squared over 2. If we want to displace to a new axis, like this, where I have some distance L, then our moment of inertia is just the center of mass inertia plus ml squared. And so we can see that each one of the disks we can treat this way. And in fact, because it's the same on both sides, we can double up much. So we can see that our moment of inertia is going to be the sum of all our little inertias, which in this case is going to be the inertia for the center guy, plus 2 times that for 2 times that for the one that's next to it, as there's 2 of them. So that would be mr squared over 2 plus ml squared. So L in this case is the distance, so that's just this 2R. Okay, and then now there's 2 of the next nearest neighbors. So plus 2 mr squared over 2 plus m times 4r squared. And there's 2 of the next nearest neighbors. And 2 of the next nearest neighbors. Mr squared over 2 plus 8, m times 8, m times 8r squared. And again, the next nearest neighbors, and the next, and finally the last. Okay, so now there's quite a few there, and I'm just going to collect some terms here, and so this comes out to be mr squared over 2 plus 7 mr squared plus 1120 mr squared. When we do all this out, or 2255 mr squared over 2. Now we can make a couple simplifications here, right? So we said that L was 30R. So then L squared is 900R squared. And so then we can plug this in. But before we do that, we might as well use the full mass. And so our full mass is 15 times the little masses. And so our little masses are m over 15. And here as well, our r squared is L squared over 900. So if we do this, our mode of inertia is now 2255 ml squared over 27,000. Which, putting in the values for our mass and our length, times 135 grams and 1.45 meters squared, we get 23.706 grams meters squared times 1 times 10 to the minus 3 kilograms per gram. Comes out to 23.706 kilograms meters squared. Okay, so then the second part of this question just asks, oops, I forgot. The second part of this question just asks, what's the percent error if instead we had represented this as a rod? So if we had said that the moment of inertia was ml squared over 12, then we would have gotten a moment of inertia of 135. .45 meters squared over 12, which comes out to be 23.653 grams meters squared times 1 times 10 to the minus 3 kilograms per gram, which is 23.653. So it looks like an okay approximation just by eye, but it wants us to compute a percent error. So our percent error here would be the known value minus the approximation over the known value. And all of it times 100%. And so this comes out to be 0.223%. So not too bad. Significantly less work and not too bad an approximation. Okay, so if we check through the solution here, we get 0.02371, so that looks pretty good. And if we approximated this, In this way, we would get 2365, which looks pretty good, or 0.02365. And the percent error would be about 0.22 or 0.25. That would be just rounding differences, I assume. So this looks good.